Claudio Tebaldi from
Thank you, David.
Bocconi in Milan.
No, it was not. Yeah.
And he is going to present to us on something which is honestly incomprehensible from the title. I mean, I know what it is, but he's going to explain to us what it is.
Okay, should I? Okay. It's not good. Yes, perfect. Thank you. So thank you to the organizers. It's really, the best way to honor Peter. And just a little bit, preparing this talk, I've been thinking the first time I met Peter, it was quite a long ago, something like, I think more than 15 years ago. It was a conference in East Midlands at Leicester, organized by Sergei Lewandowski. And there was, the reason I'm remembering is we had a fantastic lunch with Dilip and Peter. And at that conference, there were a lot of financial economists, Lars Hansen before and Schenkman before Lars got the Nobel Prize. And, they dedicated a lot of time to my Wishart model, and we had a lot of time to interact with these people. We were super friendly. But then, I do a jump of 15 years, and I would like to tell you about more recent facts. Essentially, the last time I saw Peter, we met Peter in person, was March 2020. Actually, Peter saved me and my wife from the first wave of COVID, because if you remember, COVID was first spreading in Milan, in Italy, and in Milan in particular. I just concluded my exam flying here to get the BQE seminar. And that was the start of a nice interaction. There was a weekly meeting every Sunday with Peter. Sorry for Peter's family, but it was a great meeting for me. I still miss this meeting. The meeting was, now I'm more in a true finance department, not even more math finance, a true finance department. But, with Peter, we had this feeling of moving back and forth. I teach theory of finance between financial economics, first year CAPM, and something like that, and the methods of theoretical physics, quantum physics. And he had a precise idea when we decided to interact on these topics. I didn't realize at that time how well he knew the mathematics of quantum mechanics. He knew so well that I had to go back and look at my notes from the early days of the PhD to interact with him properly. We had a lot of fun. I think, January 23rd, he produced a draft that is essentially the draft I'm building on. And I think, usually I'm pretty skeptical when you try to transfer from theoretical physics to quantum physics directly to financial economics. There are very different sciences and so on. But I think, I'm convinced, and I hope I can convince also you, that it was a non-trivial way. It was great lateral thinking. They had Peter. Peter was respected by Lars Hansen, by Steve Ross. And, the original idea, this is what he told me, is that about this parallel, you will see, we will talk about quantization in mathematical terms in a serious way, maybe good for quantum computing looking forward. So he's opening, his legacy is opening a new bridge. He got this idea when he was at the memorial of Steve Ross, because Peter was one of the early people who really understood this recovery theorem. That was the last contribution by Ross. And in fact, you will see in the Journal of Finance that he thanks Peter, Steve Ross. And here you have to go back from the super nice ideas of Julien. Here we have to move back to essentially the geometry of first year financial calculus, Capin and Markowitz. But you will see how nice math and quantum mechanics shows up within this setup. Picture is better than many words. So I just want to give you the idea it's let's think about this like a toy model, but it's a very useful toy model for financial economists. The idea, this is you see, this is a Journal of Finance picture by Tobias Adrian, Crump, and Vogt. This is a purely empirical assessment. They run a sieve regression. What's the idea? On the y-axis here, you have the Sharpe ratio, a quantity that is the expected return ex post, so ex post realized return for a zero cost portfolio divided by the volatility. But you see here, you are plotting a curve that is conditional. So you are conditioning on a variable. In this case, you are using VIX, the level of VIX. So ideally, you are thinking like VIX representing the state of the economy, the state of the market. And you realize that there is a strongly nonlinear dependence. You see here, you have two portfolios. One is essentially the benchmark market portfolio. And you see, as you would expect, this is the Buffett mantra. So, your risk return trade-off is going to improve when the blood is in Wall Street here, when the VIX is at 50. And in a way, you have a second, possibly the correlated portfolio, 1 year treasury, and the value of the Sharpe ratio is going down precisely in this way. And the basic idea here is that you have a quantity, the risk return trade-off, that is conditional on a state variable. And you want to see whether you can find the proper formalization for such a situation. It may look silly, right? Because everybody thinks in terms of a risk return trade-off like me and sigma for some diffusion and so on. But on the contrary, this is lateral thinking. It's far from obvious describing this curve here. So you have to go back to understand the full story to the original Ross 1976 paper, where he put forward a simple argument. What's the sufficient condition, to have a linear risk return trade-off in an ideal one-period economy? People had derived under the CAPM, under equilibrium conditions, strong preference conditions. What Ross observes in this paper is that you need far less. You need simply that to check, that's a sort of no arbitrage condition, a prototype of no arbitrage, by the way, that you need to check that any portfolio that has zero risk and zero pain, in the word of Peter, or zero risk and zero cost, must have non-positive expected gain. Okay, it must be zero because otherwise you can flip and you get a positive, you take the opposite position. And what Ross can prove, this goes, it follows the black version of CAPM, is that this condition is sufficient to have a well-defined ratio, a so-called linear risk-return trade-off. Okay, and by the way, the idea of the picture you see is that you have a linear risk-return trade-off you would like to have, but this should be conditional on the level of the VIX or of any other state variable. To say the complete truth, going back to our friend Lars and Hansen and Richard in 1987 have a super complicated econometric paper written in terms of a Brian-Cat notation for the quantum mechanics, where they state that this finding by Ross and then formalized in Hilbert space by Chamberlain and Rothschild can be extended to a situation where you want to condition on exogenous information. By the way, here I'm thinking about VIX as a proxy, but we should eventually condition on the level of VIX, on the level of as many variables as we would like. But this paper states a very nice existence results. The truth is that it's like a chimera, because most of the people in the financial econometrics literature, when they try to estimate these quantities, they have real problems, hard problems. So the contribution here, the idea by Peter on this is that you can rely on the Feller one-dimensional semi-group, the classification of one-dimensional diffusion by Feller that is largely well known in the math finance community, to extend and to implement the Hansen and Richard construction. I would like to stress something I didn't have the time to stress with Peter. There is something more, because while everybody that implements Hansen and Richard are relying in terms of Hilbert spaces. Here we have a sort of different construction. It's more about algebraic geometry. I cannot go deeper in this, but it's about an algebraic geometry notion that is a module. It's like a vector space, but instead of having a field, you have a ring. But Peter could spot that, he didn't know modules. That's what he told me, but he could understand that essentially the construction is implicit in the Feller papers. Okay, so this is the financial interpretation that has now also a name. It's a sort of a Sturm-Liouville module construction. So let me briefly recap. So I'm not going, the analytica, these two papers, Feller 1952 and Feller 1957 are wonderful papers. Everybody, I think, in finance has seen this classification. I'm not going to go deeper into the analytical details. Everything is in those papers. I just go through the geometry. So let's think about X as our conditioning variable, and it is assumed to follow this standard one-dimensional diffusion. The basic classification of the diffusion, the semi-group that is generated, that corresponds to the flow of the solution to the STE, is now classified in terms of two functions. One function, one measure is the scale function and the speed measure. These are defined in terms of the generators, the drift and the volatility in this way. The generator of this diffusion, so the linear operator corresponding that generates the semi-group, can be written in terms of two differential operators, d over ds, d over dm. Think about, if s and m are differentiable, you have a sort of absolute continuity relationship here. Well, think about this like derivatives scaled here by the scale function m, scaled by the m function. So these are appropriate scalings. But the important point is that all the properties, the existence properties of the semi-group can be reduced to the characterization of the domain and of these two functions. In particular, you see the second order generator, differential operators that generates the semi-group, can be written like a composition, a factorization. This is the factorization, the 1952 factorization of the generator. Okay. And now we move back to standard arbitrage pricing theory. So we want to formalize the idea of having a market conditional on the level of your state variable. And the idea is that, you think about each security, Q, with Q is the cost or the quote. I will tell you later why he's calling Q and P, these two quantities. It's related with the Q and P in quantum mechanics. But let's call this the quote of security I. So you think about QI like the price you have to pay to take a position conditional on being X, the state variable X. So this is the traditional condition saying that if you want to have a portfolio conditional on X having zero cost, the sum of I of HI QI must be zero. Okay. What about the risk? Here we introduce a little bit of a functional analysis, let's say in this way. So we introduce a notion of a risk operator. So what is a risk operator? Think about B like acting like a differential operator that acts on the quote function. And the basic idea is super simple, right? Because the idea is that if you want to know what's the risk associated with position Q, you shock Q with respect to X. So you think about having a small shock to the state variable X, and you see what's the variation in the price. It's like a delta, but crucial observation by Peter, you need to scale, we'll see why, by S prime. So it's variation, the so-called first order variation, but then you scale by the scale function, the marginal variation of the scale function. And now, finally, you can state now your super simple, going back to Theorem, here we are trying to deconstruct. We have a local, this is a super local in physical terms condition, condition for no arbitrage. What's this condition? It's saying that if you don't have zero cost and zero pain, you must have zero gain. Okay, so how do you define the gain? Here is a mean gain rate, GI. You define GI simply thinking that given G is your semi-group generator, you apply G to Q and you will have the time variation
of the price, of the cost for this portfolio. And this is what you think about like a mean gain rate, the time variation of price, that is a measure of your gain. Okay? And notice that, by the way, you see that essentially G can be written also like the speed differential operator applied to the pain, to the risk. Okay? Now, here is important. This condition can be read, by the way, think about this. This is the notion of matrix mechanics from quantum mechanics. Think about this like a statement about, let's say, the operator G, the operator B, and then you may think you have an identity operator here that will be the cost operator. So we can set up a linear system where essentially you are thinking that this is a linear system. You see, think about G, I, and B like matrices. Think about lambda and lambda 0 and lambda 1 like, if you want scalar vectors or elements of a vector space. So you see, this is maybe you don't remember, but this is from linear algebra, from a basic linear algebra. The condition of no arbitrage is a necessary condition for this system to have a solution. And in addition, it's also sufficient if you are, say, in a vector space, if you think about a finite dimensional setup. Okay? But indeed, relying on the failure classification, you can easily find a way also to define, to find the conditions on lambda 0 and lambda 1 that make this condition necessary and sufficient. So what's the outcome here? The outcome here is that now you have an operator relationship here that involves G, the mean gain rate operator, the cost operator, and the risk operator. You have two coefficients. You can write, you can drop a QI, think about QI like your basis, and you get a condition that is the condition that is necessary, sufficient, is equivalent to this no arbitrage condition. But notice that this condition is exactly the counterpart to the Ross linear risk return trade-off, because the mean gain rate corresponds to the expected return. The lambda 0,1 corresponds to the cost operator. The lambda 1 is what you would call the risk, this is related to the risk adjustment. B, I wrote B because, by the way, B is the risk operator that would correspond in the Ross notation to the beta. Okay? And here we realize that the analogy with quantum mechanics is mathematical, because quantization in mathematics, we have now a quantization theory, is moving from numbers to operators while preserving some symmetry, some algebra. In the case of mechanics, you preserve Hamiltonian, the flow of the Hamiltonian mechanics, the Hamiltonian geometry, the so-called symplectic geometry. Here you see that you are transferring the geometry of, let's say, of the Fredholm alternative of this linear compatibility condition. That is what we use to implement the no arbitrage in this setup. Okay, and so we really, by the way, we can go on with this analogy. Okay, so how can we go on with this analogy? Well, the idea is this lambda 0 plays the role of sort of risk-free rate or something like that. So the important issue here is that from a Markov point of view, we are moving, if you have this term that is constant, we are moving from a conservative differential operator, one that has no constant term, to one that is non-conservative. And this is a challenge. But anyhow, the idea is that you can at least think about moving this lambda 1 on the left. So you adjust by risk the scale and the speed measure. So you eat in the definition of M hat and S hat your lambda 1, and by risk adjusting, you have a sort of risk neutral variation of the same argument, right? Why it's risk neutral, this new factorization? Well, because now you see that all the securities QI that obey the no arbitrage condition must have the same mean gain rate. So here we moved in a setup where we have again a functional equation, an operator equation, but this equation is now a sort of risk neutral like equation. This is clearly related with the gauge transformation that mimics the Girshanov transformation. Now, the lambda 0 is a potential, so it's a quantity that goes out from the 1952 classification of diffusions by failure. But here is, again, a nice observation. The nice observation is that in failure, there is this 1957 paper. He observes that the classification of one-dimensional semigroups can be extended beyond conservative diffusions by considering a very special form of non-conservative diffusion. So what's the idea? Here, the idea is that, well, instead of considering a common mean gain rate, sorry, I got lost. Okay, here you see, instead of putting a lambda 0 here, you assume you have a positive numeraire, Q0 of x, a spatial security that has a positive value. You replace the lambda 0 by this ratio, and you can rewrite this operator. You can embed also the lambda 0 on the left, and you can define this L of Q0 that is a new second order differential operator, now defined in terms of a Q0, a numeraire. And now all the securities that obey the no arbitrage principle must be within the null space, the space of the kernel of the linear operator LQ0. And the nice final observation here is that, well, this has also a very neat interpretation in terms of financial terms. What's the neat interpretation? Well, Q0 now is our numeraire. Let's think about a sort of benchmark, possibly a risk-free security. We can then define a risk-adjusted, an adjusted risk operator. What's the meaning? Well, think about the CAPM. So in the CAPM, when you introduce something that is close to a risk-free or a zero covariance beta or a benchmark security, well, you start measuring excess returns rather than returns. So here, you normalize by Q0, you will have Q over Q0. When you compute the risk, you apply B to compute the risk for a generic Q portfolio. Q over Q0 will play the role of the price discounted at the risk-free rate. So this is an adjusted risk operator. This is an important observation. You can work it out. You realize that this is, in the financial interpretation, the risk of a zero-cost portfolio. In a mathematical interpretation, this is the so-called Wronskian associated to the second-order differential operator. And by the Liouville theory, you know that once you know a positive solution, you can get another solution linearly independent. Now you have a second-order differential operator, linear. You know that the space is spanned by 2. So what you can get from this is that, bottom line, you can identify two portfolios, the risk-free portfolio, some benchmark portfolio, remember the first curve, and you have a mutual fund theorem, okay? So the idea is that now this kernel represents the market, the one that the cost function that satisfies the condition of no arbitrage. The level sets of the Wronskian operator represent securities which have the same level of risk. By the way, you can set by convention the level of risk at the level beta. You decide that you have a benchmark security with beta equal 1, that will be your proxy for the market. Any other security can be represented as a linear combination by linearity of B. And what you get is a linear security market line, a conventional security market line, now written in terms of cost functions, conditional on X. Last but not least, just to conclude, why this theory innovates, generally speaking. By the way, we would love to extend, we had the idea about extending this conditioning on more complex variables, on T, on volatility. But the basic idea here is that, well, if you reconsider the linear algebraic compatibility condition, well, you realize that this condition, now you have zero cost, zero risk portfolio. This is your kernel for the arbitrage. Well, you must have an operator M. Sorry, here is Q0 minus 1. This is what Peter called the monetization operator. What's the dimension of this operator? Well, B is risk. L is a expected return for expected excess return for a portfolio. M is the functional, the operator expression for the Sharpe ratio. So the main idea, this is in the words of Peter, is to treat market price of risk and amount of risk as linear operators rather than as numbers. So this conceptual leap is identical. You know, Peter wanted to get convinced that he worked out also the matrix discrete version of reformulation of mechanics using matrices as recognized by Bohr. Okay, so this is the functional object, the operator that describes the picture we have seen in the first slide. So, you know, here, some comment, an important comment is that we have looked at these Feller papers from a completely different point of view. This was lateral thinking. It's based on geometry. Here we are doing something much more similar to geometry. It was great fun. It was great fun for sure. By the way, Peter did fun, but it also progressed. They did progress, and I hope I want to think Peter is smiling like here and looking at our conference. Thank you.
So thank you, Claudio, for a fascinating talk and a beautiful picture of you with Peter. In the interest of time, let's skip the questions and go straight to Pasquale Cirillo.